First of all, thank you to the organizing committee for all the hard work putting this together. I was actually here the first Network Frontiers, and it was really fantastic. Fortunately, I had to miss a couple after that. But so today, I'm going to be talking about directedness in networks and how, or I'm going to argue that it promotes synchronization in networks of heterogeneous oscillators. So this is work I've done mostly in collaboration with Dane and Rio. A little bit as well with Alex Arenas, who's my postdoc advisor when I was back in Barcelona. Before I get to heterogeneous oscillators, I want to talk quickly about identical oscillators for some motivation. And Rio actually did a good job of introducing this for me. The sort of main problem setup, many of you guys will recognize. We have identical oscillators X with the internal dynamics given by this vector field F. The coupling function is H and the coupling strength is K, and the Laplacian L really sort of encapsulates the network topology. Of course, the big breakthrough came in 1998. I was actually in 6th grade at the moment. But when Lou and Tom came up with the master stability function approach, which is basically the largely up and off exponent of this system here, and the main idea is that you want all of your eigenvalues scaled by your coupling strength to fall in the the stability region where that largely up and off exponent is negative. I've lifted this graphic here from one of Takashi and Adelson's papers because I think it perfectly sort of shows what you need here. So you need some sort of medium scaling there. If you think about it just a little bit, then really the best possible network, like Rio mentioned, is one where all of the eigenvalues, all the non-trivial eigenvalues are the same. And it turns out that is the case when you have a non-diagonalizable network. And of course, to be not diagonalizable, you need directedness in the network. And that's sort of where I want to connect with today. So I'll be looking at heterogeneous oscillators and specifically sort of Kerr-Moto oscillators. So you have different natural frequencies for the different oscillators, and I'm using sine as the coupling function here. So I'll note that you can generalize all this to some other kind of tube high periodic function, but I'll stick with the Kerr-Moto case here, and I'll look at synchronization as measured by sort of the typical order parameter. This complex number here with magnitude R, and R is going to be sort of the thing that we really care about. And so we're going to sort of see cases that vary between different sort of situations. On the left, there's not too much synchronization going on. On the right, you have a little bit more. We don't expect to see perfect synchronization because the frequencies are actually different. And so that highlights the key point here that differentiates this from the identical oscillator case, which is there's an interplay sort of between the heterogeneous frequencies and the network structure. And we can ask all sorts of questions about that, like optimization, synchronizability, that sort of thing. So I'm going to sort of skip some of the mathematical pieces. But a few years ago, Rio and Dane and myself, we were looking at optimizing networks for synchronization, i.e. basically maximizing the order parameter. And so we came up with this thing called the synchrony alignment function. And essentially what we did was we linearized around a strongly synchronized state, and we found that you could write down the order parameter using this function J. And this J is a synchrony alignment function. And that's just a function of the natural frequencies and the Laplacian matrix. So over here you really have this sum of projections of the natural frequency vector on the non-trivial eigenvectors. Those projections squared and then scaled by the square of the corresponding eigenvalues. Now note that to optimize synchronization here, you want to minimize J. And if you look over at sort of how this function is organized, what you really want is to have your natural frequencies aligned strongly with the dominant eigenvectors, thereby sort of minimizing this J. So we found that it was surprisingly, or maybe not surprisingly, but it was really effective in a lot of sort of constraints, a lot of different situations. Here's one just as an example. where we have a fixed network and a fixed set of frequencies, and all we're allowed to do is sort of move the oscillators to different points on the network. So if you do that randomly, you get a kind of mild, not so great transition to synchronization. But if you do that optimally, you get this really strong transition to a really sort of strongly synchronized state. So we want to sort of explore the directed case here. So specifically, what I want to do is sort of consider the analog of this identical oscillator question of whether directed networks are in some sense better. And now, I think there's sort of an intuitive reason as to why this might be true. So take a network that looks like this, and first note that any undirected link is just a pair of equal and opposite directed links, right? And so if we have a network like this where we have two oscillators that are connected and a third that's not connected to either one of them, then if we take one sort of these directed links, for instance, the blue one, my claim is maybe there's some sort of diminished return in terms of what we're getting out of this link. So for instance, if we reroute this just a little bit, maybe to this third node, maybe we get some more bang for our buck. And of course, this is very hand-wavy, but I think there's some intuition as to why this might increase sort of synchronization. Now, to get after this, we need to generalize sort of the theory, and we can do that. So the synchrony alignment function, it looks very similar for directed networks. The key difference, though, is that instead of eigenvalues and eigenvectors, and those are the things we used for the undirected case, what we're using here are singular values and less singular vectors. Right? It's sort of like the crux of the issue at this point. So there's a few things that come out of this. So the first is this notion of a collective frequency. So the collective frequency is really the frequency at which a synchronized state, if everything is synchronized together, will move, right? So there's capital omega if I write things down in this way. And if you just kind of guess at it, then you might expect that this is exactly equal to the mean of all the natural frequencies. All right, and there's no reason to think otherwise. And that's true for undirected networks, but it actually turns out that that's not true for directed networks, which is kind of surprising. So the reason for this is actually quite simple, and again, I won't show any of the mathematical details here, but in the undirected case, your trivial eigenvector is just constant. And so the collective frequency, you can actually calculate it as the ratio of these two projections, the frequency vector onto this eigenvector, and then basically the sum of the eigenvector entries, and that's just a mean at that point because the eigenvector is constant. Now, in the directed case, we don't have that eigenvector anymore. We have that first left singular vector, and that is not constant. And when you use that in the same way, what you effectively get is a weighted average, not a mean. And so the actual frequency with which your network is going to move after it synchronizes is not equal to the mean frequency, or the mean natural frequency. So here's just like a toy example of this. Here the mean natural frequency is 0, and we took a bunch of cases where we just took and mixed natural frequencies around on this very small network, and you can see you get a whole bunch of different collective frequencies, both positive and negative. So how does this actually sort of correspond to synchronization in general? We're going to use this setup of the synchrony alignment function, and specifically I'm going to, in the J function, first of all, just ignore the contribution of the singular values, and I'll get back to that. But if I look at that sum of those squared projections, then you can actually write down that that is the norm squared of the frequency vector minus the squared projection that you're sort of missing in that sum, on that sort of first left singular vector. And now the idea is to not imagine a case for a specific frequency vector, but sort of an average over a bunch of different ones. So if I have my synchrony alignment function, And if I just choose a completely random frequency vector, then I can approximate this by kind of pulling apart that sum, and I get these two pieces here. And in fact, if I actually then just do a sort of a proper average over all frequency vectors that have that norm, then I get these two terms, all right? And so the argument at that point is that on average, a network's sort of synchronization is going to be promoted when these two terms decrease, all right? And so we can say a little bit about both of these terms. First of all, this first one on the left here, it's directly connected to this collective frequency that we talked about just a few slides ago. And in particular, if I look at that first left singular vector, then with a mean field sort of approximation of the network, you can write out that's approximately the ratio of the out to in degree at every node. Now that means that this projection squared is about the variance, is about proportional anyway to the variance of those quantities. Now the key here is that in an undirected network, the in and out degree is always the same, so that variance is precisely 0. But when you have a directed network, that variance is going to increase, all right? And that'll basically make this term on the upper left here smaller and promote synchronization. For a given network, we can sort of measure more or less how directed it is by really just counting the fraction of links that don't have sort of an equal, directed links that don't have an equal and opposite sort of directed partner. And in fact, this quantity here, that projection that we're interested in, actually increases pretty well with directedness. This last piece here, the sum of the inverse squared of the non-trivial singular values, is a little bit more complicated actually. So this is a quantity that we thought would be pretty easy to approximate at first, but Dane and Rio and I have been kind of scratching our heads over this for well over a year at this point. We actually have a pretty good description of it now. I'm going to have to sort of not share that at the moment. We're in the process of organizing some stuff, so you'll have to stay tuned for that. But what we can do at the very least is just show what sort of some simulations results in. And you can sort of see with the directedness in a network, this quantity does also decrease. All right. So in fact, both of these quantities that should decrease tend to decrease as directedness increases. And so let's just look at sort of the order parameter, the straight up synchronization properties without approximation. So what we did was we took Erdős-Renyi networks because we didn't want any sort of other network structures to play a role in what was going on. So of course there's no hubs, there's no community structure, there's nothing else. So if we change directedness, we can be pretty sure that that's really the only thing that is changing. And in fact, when we make Erdős-Renyi networks more directed, then the synchronization properties increase quite a bit, relatively speaking. And so here's just sort of a zoom in of that. And so what I really want to argue here is that directedness tends to promote synchronization in heterogeneous oscillator networks. This is kind of an analog to the identical oscillator case, but I think all of the pieces here are quite different in flavor. So there's sort of a similar result, but the way that you get there is quite a bit different. So that actually brings me to the end here. So here are just a few of the references for the work that this was based on. The specific sort of thesis, I guess, of this work is to come still, but I will be more than happy to take any questions at this point.